In this lecture, we want to look at some examples of first order RL and RC circuit response. We'll look first at circuits with a natural response, and then we'll look at the step response. So here's an example of a circuit we're asked just to find the time constant for the RC circuit. This is just some practice. It is an RC circuit even though there are multiple resistors, because there is only one capacitor. So the capacitor here by itself means that we have a single capacitor, so this is going to be what we call a first order RC circuit. Now what you want to do in order to find the time constant is you basically want to find the Thevenin equivalent resistance as seen by the capacitor. So if I look at these two terminals, that'll be the capacitor's perspective on what the circuit looks like. In order to find an equivalent resistance, we need to kill the voltage source, which means we're going to short it. So we have 120 ohms now appearing in parallel with 80 ohms and 12 ohms, and then our capacitor is sitting here looking in at this equivalent resistance. So we have 80 in parallel with 120. I believe, if I'm correct, that's going to be 60. But let me check here on my calculator just to be sure. So we have 80 times 120 divided by 80 plus 120. So 80 times 120 is 9,600, and if I divide that by 200, I actually end up with 48. Okay, so that's 48 and 12, and then here are my terminals. So our equivalent is 12 plus 48, or 60 ohms. So 60 ohms was the total. Alright, which means our equivalent R is 60 ohms, our capacitance is 200 millifarads. So tau, our time constant, is 200 millifarads. So we'll go ahead and move to scientific notation here. And then this is my C, and this is my R. And when I multiply those together, I should get 12 seconds. Let's see, is that right? 6 and 2, that's 12,000, or 12 times 10 to the third times 10 to the minus third. They cancel out, so it looks like I'm going to get 12 seconds. So moral of the story here on this example, you have to combine all of your resistors into an equivalent resistance. Now, I just want to briefly look at what would have happened had we had a slightly different situation. Ohms. Let's suppose instead of a single capacitor, we had two capacitors in series. And we'll say they're both 200 millifarads, 200 millifarads. And same problem here, we just want to find the time constant. Now in this case, even though we have two capacitors, because they are in series, we can combine them. So I can combine those two in series to get a single 100 millifarad capacitor, because remember, capacitors in series combine like resistors in parallel. And then I already know that my equivalent resistance is 60 ohms. So in this case, this is still considered a first order circuit because these two capacitors are in series. Let's look at a case where you could not combine two capacitors. So suppose I have some resistor and some capacitor, and then I have another resistor and another capacitor. In this particular case, for the kind of transient analysis that we're doing on first order RC circuits, this is not a circuit that can be simplified. If you note, there's no way to combine the resistor and the capacitor here in series because there are two different elements, two different sets of units, and as we're analyzing circuits right now, there's no way to combine that. In circuits 2, and also when we get to AC circuits, which will be next week hopefully, there is a way to do that, but in this particular type of analysis we cannot. So this would not be a first order circuit. This one would be, because we've got two capacitors in series. Alright, let's look at the next problem. So this is a problem where we actually have a circuit with a switch. It says that it has been in position A for a long time. So what does that mean? That means that for t less than 0, so for t less than 0, the circuit looks like this. 5 kiloohms. At position A, you'll notice that this 2 kilo ohm resistor is just dangling, so it actually doesn't enter the circuit. Now, because it's been sitting for a long time, the circuit appears to be DC. Remember we said after 3 to 5 time constants, the transient effects for RC circuits are gone. And so you basically then have a DC type situation. So capacitors look like open circuits under DC. So this is the voltage across the capacitor for what we will call 0 minus, meaning the switch has been sitting in position A for a very long time. Right before it moves to position B, we use this little minus notation. Okay, you don't have to use that notation. You can say V of C for t less than 0, but or for t at 0, but really 0 minus is a standard terminology. We'll use it in circuits too. You'll use it a lot, so I want to get you familiar with it now. So at 0 minus, right before the switch moves, this is an open circuit, no current flows. The voltage drop across the 5 kilo ohm is going to be 0 because there's no current. So here at this open circuit, the entire 40 volts from the source appears. So VC at 0 minus is 40 volts. Now what is that? That's the initial condition on that capacitor voltage. Okay. Now what we need to do is we need to find out what happens after the switch moves. So for t greater than 0, or greater than or equal to 0 plus, meaning the moment that the switch moves to position B, we have the following. We have a 2 kilo ohm resistor and a 10 microfarad capacitor that had an initial voltage on it of 40 volts. We know that because the voltage across the capacitor is not allowed to change instantaneously. So if it is 40 volts the instant before the switch moves, it is 40 volts the instant after the switch moves. So now what we have is the natural response. So tau, once again, is RC. So it's 2 times 10 to the third, 10 to the minus 6. So it's going to be 20 times 10 to the minus third, or 20 milliseconds. Okay. We'll just leave it as 20 times 10 to the minus third. We'll leave it in seconds. Okay, V sub 0, which is the initial voltage, was 40 volts. So we know from our standard natural response of an RC circuit that V is a function of time is V sub 0 e to the minus t over tau. So we can just fill in the blanks. It's going to be 40 e to the minus t over 20 times 10 to the minus third volts. Okay, and that's it. So that is how we work with finding initial conditions. Let's look at another one. Okay, so in this problem we have the same kind of thing. We have basically a situation before the switch opens and a situation after the switch opens. So before the switch opens, so for t less than 0, or t equals 0 minus, right before the switch moves. we have 6 volts, 2 kiloohms. The switch is closed, 4 kiloohms. And the capacitor, because it's been sitting for a long time, is open. So the voltage across the capacitor is the voltage across this open circuit, which is the voltage across the 4 kiloohm resistor. So doing voltage divider, V sub 0 will be 4 over 4 plus 2 times 6, which is 4 volts. So now let's look at the circuit for t greater than 0. So once again, the voltage across the capacitor does not change instantaneously. So the initial condition after the switch moves is that we had some voltage, V naught, that was 4 volts. We have 3 millifarads. We have 4 kiloohms. So V of t is V0 e to the minus t over tau. So what we need to find is tau. So tau is RC, so it's 4 10 to the third, 3 10 to the minus third, so tau is 12 seconds. So V of t is 4 e to the minus t over 12. Now, if you'll bear with me for just a moment, I want to talk about what we looked at when we talked about the step response, and that is that there is this general formula that works sort of for everything. So remember we had this formula, x of t, where x was our variable we were solving for, was the final value of x plus the initial value of x minus the final value of x, e to the minus t over tau. So let's say rather than applying our formula for the step response of an RC circuit, we apply this formula instead. Well, we know, for example, that as t approaches infinity, then this RC circuit here will have been sitting for a very long time, and the energy that was stored in the capacitor will have been dissipated through the resistor, because, as you know, we know the characteristic natural response for an RC circuit looks like this. It's going to drain away to 0. So the final value approaches 0 or equals 0 at infinity. The initial value we've already solved for. And by the way, in this case, our x is V. And so x final is V across the capacitor final is 0. X initial is V initial, which was 4. And tau, we already know, is 12. So we're going to plug this in for V final, and we'll go ahead and rewrite this. V of t is V final plus V initial minus V final e to the minus t over tau. And then we're just going to plug in for each variable. So this is 0, this is 0. So we're left with 4 e to the minus t over 12, same thing, volts. So just to illustrate to you, hopefully you've watched the previous 2 videos, so just to illustrate that this formula yields exactly the same answer if you go with the formula specific for the natural response. Okay, now I want to look at another example, and this one is an RL circuit. So let's look at the RL circuit. So initially, once again, we're going to analyze this circuit first for t less than 0. So here's 24 volts. T less than 0, the switch is closed. So the switch is closed. And the other thing about t less than 0 is that the inductor at 0 minus looks like a short. So the inductor is here, but it looks like a short. Okay, let's do a source transformation on that 24 volts and the 4 ohms. So I'll get 6 amps. That 4 ohm resistor moves in parallel this other 4 ohm resistor is still here, and my 8 ohm resistor is here, and the inductor is still looking like a short. So what I want is, I want the current through the 8 ohm resistor. Okay, these two 4 can be combined in parallel, so 6 amps. And when I do that, I'll get 2 ohms. And then here's my 8 ohms. Here's my I0. So using current divider, I0 is the current through, is the other resistor, 2, over the sum, 2 plus 8 times 6. So it is 0.2 times 6, or 1.2 amps. And that makes sense because we would expect the lower amount of the 6 amps to go through the 8 ohms because it's a bigger resistor. Okay, so our initial condition on the current is 1.2 amps. Now let's look at what happens for t greater than 0. So the switch is opened. We have our 4 ohm. This entire left part of the circuit is out of the problem now. We have 4 henries. We have 8 ohms. And in order to find the time constant, we need to reduce that to a single resistor. And then here is our I of t, and we have an I of 0. That was 1.2 amps. So simplifying the circuit further, 4 henries, just combining the 4 ohm and the 8 ohm resistors to get 12. Here's I of t. So I of t, according to the formula for the natural response in an inductor, is is I0 e to the minus t over tau, and tau for an RL is L over R. So given that, we can calculate, we know I sub 0, and we can calculate tau. So it's going to be 4 over 12, or 1/3. I can leave it 1/3 seconds. So I of t is I sub 0, which we already found to be 1.2 amps, e to the minus t over tau, which is 1/3. And we can flip that around if you want. I of t is 1.2 e to the minus 3t. Now 3 is no longer tau. 3 is 1 over tau. Some people like to express it this way. If you express it like this, where you have tau in the denominator, tau becomes easily readable. And so if you wanted to plot this, you could pick units of 1/3 of a second. So 1/3, 2/3, 1. This would then be 3 time constants. It starts out at 1.2. It drops to about 36% of that, and then it drops to about 36% of the previous value. So you could sketch that kind of eyeball sketch. Okay, I think I might have one more example, maybe 2. Yeah, so here we just want to calculate the time constant. So this is going to be similar to the problem where we're just looking for an equivalent single R and single L in this circuit. So we have 20 and 40 ohm in series, so let's combine those to get 60. And then here is our 5 millihenry inductor, and here is our, and by the way, that is kilo ohms, and a 30 and 10 in series would give us 40 kilo ohms. And now you notice everything is in parallel, so we'll combine the 40 and the 60. And if I do a quick calculation on that, that's going to be 40 times 60 over 40 plus 60, which I believe gives you 24 ohms. So our final circuit, and then it's kilo ohms, I'm still in kilo ohms. So our final circuit has 24 kilo ohms and 5 millihenries. So tau, which is L over R, will be 5 times 10 to the minus third over 24 times 10 to the third. Okay, so if I do that, that's 5 divided by 24. So I'm getting 0.21 times 10 to the minus 6, which is sub-microsecond time constant. So the question is that unusually small? And the answer is no. Microseconds, as far as time constants go, is not necessarily considered a super small number. Alright, I think the last example I want to work is here. Here we're actually given the initial condition on the inductor current, and we're asked to find the inductor voltage, the inductor current, and then we're asked to find this V of t. So the first thing I want to do is I want to find the time constant. So what does the inductor see? And then given the initial current and a time constant, we can find the inductor current as a function of time. So to find a time constant, I need to do some combining. So I'm going to combine the 5 and the 20 because they're in parallel. So this is 5 parallel 20. If you do that, the result is 4 ohms. I then have 2 henries. I have I of t. I have I at 0 is 10 amps. And I have my 1 ohm. So now you can see everything is in series, so the 1 ohm and the 4 ohm add. I'm left with 5 ohms and 2 henries. So I can now write out I of t is I0 e to the minus t over tau, where tau is L over R, which is 2 over 5 or 0.4. I naught was given as 10 amps. So I of t is what? It is it's 10 e to the minus t over 0.4 amps. So that is my inductor current. Okay, now if we look here, okay, this current, this I of t, splits between the 20 ohm and the 5 ohm resistor. And so we can actually, given that we know the value of I of t, we know the total current entering the node where we have 2 parallel resistors. So we could find the current through the 20 ohm resistor by using current divider. So let's call this I2 and this I1. So I2 is my total current, which is 10 e to the minus t over 0.4 times the current divider ratio, which is 5 over 5 plus 20. Okay, so if you simplify that, that's 2.5 e to the minus t over 0.4. That's I2, and we've defined I2 as going up. Now, if you look at the way the voltage is defined, according to the passive sign convention, the voltage is defined in this way. So the actual current I, if we're going to use Ohm's law and actually solve for V of t, V of t is I, and let's call it I of the resistor. It's I of the resistor times 20 ohms, but notice these two are opposite in direction. So what I'm going to do is I'm going to plug in a negative 2.5 e to the minus t over 0.4 because it's flowing in the opposite direction of what I solve for based on the definition of the v of t that I'm solving for. And then I need to plug in the resistor value of 20 ohms. So when I do that, I get minus 50 e to the minus t over 0.4 volts, and that's going to be the voltage as defined with this polarity across that 20 ohm resistor. So one thing that I want you to notice is this e to the minus t over 0.4 term. That's going to be common for all currents and voltages. So in other words, if one part of your circuit, like this inductor current that we solve for, behaves in a transient fashion, then every part of the circuit behaves in a transient fashion. So that natural response of the circuit will be common to every current and voltage in the circuit. The time constant will always be the same. The only thing that's going to change is going to be the magnitude of your current or voltage based on what you're solving for. So that concludes the example problems that I wanted